Hello and welcome to Haystack Live. This is our occasional online meetup about all topics around search and relevance. And I'm very pleased today to say we have two fantastic speakers from Otto Group, old friends of Open Source Connections, Otto Group. And they're going to be talking about how they built the autosuggest infrastructure for Otto.de. So looking forward to that. But before that, I've got a few other announcements. We have at Open Source Connections over the years trained lots of people on search and relevance. You may be aware of this. And we've actually been revamping our training. And it's now available as a self-led class using the Moodle platform. And we'll be running sessions on Elasticsearch from March the 20th and on Solar from May the 1st. Do check it out on our website. And also, I also wrote a blog last week about all the different options you have for training your search team. So check that out as well. And there's a brand new training going to be happening at the Haystack US conference, about which more later. That's going to be on search result quality, going beyond relevance. So do check that out. The URL's just there. So during today, a lot of you have been before to Haystack Live, but the way this works is I'd like you all to keep your microphones muted during the talks. If you have ideas for questions for Tobias or Tom during the talk, then please drop them into the Zoom chat. At the end of their talk, I'll be asking those questions on your behalf to make sure everyone has a fair go. And if I can't quite understand your question or want to get some feedback, I may ask you to unmute and chip in. But generally, I'll be asking those questions for you. But without further ado, I'm going to be handing over now to Tobias and Tom, who will be talking all about their journey towards autosuggest. So thank you very much, chaps, and over to you.
Yes, hello, everyone. First, thanks for having us. Let me share the screen. So I hope that everyone can see the screen. Perfect, Charlie. Thanks. We would like to take you on our journey of how we built the autosuggest for Otto.de. But first, I would like to tell you who we are. So this is Toby. I'm a software developer here in a team at Otto.de. I'm totally in love with Java, Solar, and all this Lucene stuff, all the search technologies. Around the world, father of 3 children, organizer of the search technology meetup here in Hamburg, which might be the next iteration in the next week. So let's see. Yeah, and basically I'm working the past 9 years in the context of search, and now I'm totally in love with the autosuggest. So is Tom. He's also a developer in our team, and we both are with our team responsible for the autosuggest. I don't know if any one of you knows Otto.de. Otto.de is the second largest e-commerce online shop in Germany. We're selling a lot of stuff. We're a generalistic store where you can buy anything, and everything is divided into vertical teams. So we in our vertical team, we are responsible for the autosuggest from end to end. So we are in a cross-functional team. We have front-end developers, back-end developers, data scientists, and analytics guy, infrastructure guys here and there. So being responsible for this from end to end is a lot of fun. And this is what we are doing. We are delivering all the time. So currently on Otto.de, we have at about 2.9 million visits per day. In peak, our autosuggest gets of about 400 requests per second. And in the P99, we are delivering between 20 to 30 milliseconds. So just to give you a rough understanding of what we do and on which scale you can see our autosuggest. And yes, as we already told you, we would like to take you on our journey, what we did in the past. So we had some architectural decisions, and we also had some problems. And this is something we would like to tell you today. So we started at the beginning 1.5 years ago and we started with a theme which is called, well, it works, maybe. So we took over the autosuggest from another team. And the autosuggest was completely written in Elasticsearch. So there was a very small API in front of that Elasticsearch cluster, but we had multiple nodes where we store the queries in, and that was the monolith that we took over. So this was pretty cool as a starting point, but we thought, okay, we think that we can do this a little bit smarter. So we throw out a lot of stuff, and we created a completely new application. So now the new application looks like this. The customer goes directly to our suggest application, and we just had a simple cache next to the application. This application was completely, or is completely, written in Python, and we are storing directly in a data structure. We stored our suggestions directly in a data structure in the auto suggest, or in the suggest application there. In the past, we used a data structure which is called a try data structure. I don't know if everyone is aware of that, but a try data structure is just let's say a tree, which is perfectly for prefix matching, prefix matches, because it will construct the data structure by every token. But Tom will tell a lot more about the data structure a little bit later. So back nearly 1 year ago, we had the data structure, the try data structure in our application, and everything was fine. And then in September in the past year, or one and a little bit more year ago, so we had the requirement that we would like to test this. So on AutoDE, we have the requirement that every feature that goes live to the customer needs to be tested, and we need to have a number on it. And this is how it looks like. This is just an usual A/B test. So we have two groups of customer, A and B, and we should deliver different functionalities to each groups. And so we did the simplest approach, and we added a lot of feature toggles. This ended up in a code that was hard to maintain, hard to read, and it was very hard to, if the feature doesn't work out, to remove the feature toggles again, and to remove the features here and there again. I know that there are multiple libraries out there to do this in a better way than this, but we thought a little bit about our architecture, and this is the next step. It's the plug and play step. So we thought, okay, first let's add feature branch deployment. So we did this. This was very simple with our infrastructure. And currently the process looks like this. We have an GitHub repo, and if you add the prefix feature / to the repo, we will spin up a completely new environment. So we have two suggest environments also with their separate caches. And before these applications, before these suggest applications, we've added a distribution application. In our case, this is called Prism. And this application saves us a lot, because in the suggest, we can do anything that we would like to do. We are distributing requests, and if the suggest behind the distribution doesn't answer, we will deliver, for example, a static fallback. So we are following the principle here of always delivering something. So if we are down with our auto suggest in the backend, we will minimum will deliver some static fallbacks, which are just the top 10 searches in the past weeks. And this is pretty cool, because in any case, we were delivering something. And this new architecture helps us to remove a lot of technical stuff, or to move a lot of technical stuff into the distribution layer. So we added there, for example, also some very important metrics of how long are the queries running, where do we have the most problems here or there, and we have one single point of knowledge. So this architecture enables us to have a good Onyx test and to easily create or test some new candidates out there. We've built the distribution layer completely on Kotlin and Coroutines. This was a lot of fun. And in the end, we thought, okay, the cache here on every suggest is a little bit expensive. And yeah, we don't need that. Let's move this to the distribution layer. So we thought, okay, this is a tag layer, and let's move this caching there. And we thought a little bit, how complicated could this caching be, or is this caching? And we thought caching, this should never be the problem. So we added an instance, we did the merge of the pull request, we went live, and then yes, immediately we went down. This was a lot of fun. We learned a lot in the time. For example, always take care of the database memory consumption if you are using an caching instance that might use some memory. So visibility was the key here. We went down because the caching instance just explodes. We increased that, and yeah, this was our final architecture here, which went pretty good. So we removed both caches from the suggest applications there at the bottom. And then we thought, now everything is fine. But then we added more visibility to our application. We've created a slow log with the most slowest queries in our autosuggest. And we saw a pattern. We saw a much broader pattern that if you start to type, which is in an autosuggest always the case, and we are delivering something just if you have one keystroke or one character in your search box. So, and all these queries which with just one keystroke or one character, that were very, very slow in our case. And so we thought, let's try to cache these asynchronously. So first asked our suggest application, can you deliver something in a specific timeout? The application wasn't able to deliver something, and we sent the request again within an async caching method, and we found out that Spring caching and coroutines is a huge problem. So, but we achieved it, and so this is the code you can see, which is currently running in our distribution layer. So as you can see at the top, we are querying the candidate. And if we have an exception, or for example, a timeout cancellation exception, so we ran into a timeout with the current query, then we track it for sure. This is very important. And we try to cache it again with a second request. And this is a pretty cool pattern on which we thought, or currently also think, that it's a very cool pattern that helps us to reduce a lot of long-running queries. And then we thought, okay, we did it, and we did everything. But then Tom will talk about some other problems.
Yes, hello. So we thought, great, everything works now. And then the graphs showed us this. So what is this? At the top, you see the CPU usage of our distribution service. And just at some point, it just doubled itself out of nowhere. At the bottom, you see the requests that we get. So there's also nothing really suspicious there. And one important thing is that we had an A/B test running at the time. But we always do A/B tests. So this was nothing that we found somehow strange. So we didn't think much about that. And this problem will lead us to our next section. We will talk a bit about regex. So in order to determine in which group a user is, in group A or B, if you do an A/B test, we somehow have to identify that. And we are passing a value out of a header. And we are using a pattern that is very, very close to the one that you see there. And so we are looking for some static match in this header. And what happened at the point where the CPU usage doubled is that the foo was just not inside the header anymore because our A/B test was stopped, which is completely fine. They have to stop at some point. But then the regex engine was just desperately trying to find this foo somewhere, and it didn't manage to because it wasn't there. The keyword that you can Google is catastrophic backtracking. And this basically means that we tried like tens of thousands possibilities. Our CPU really was not happy, and our customers also weren't happy because this increased our response times. And then we thought, okay, how can we fix this? Because we really needed a fix for that. And actually, the fix was quite simple. We just don't use regex. Because what we realized is, at the top left, you see the timings when we used this regex pattern. And on the right side, we just used index of. Because what do we want to do? We have a static value that we want to find inside a string. And if it's not present, then we want to handle this case. And if it's present, then we have to extract a group, which is just very simple. So we learned that if your problem is really simple, then look for some simpler solution. Regex was in our case just way too complex for the thing that we wanted to achieve. So this was good. This solved our problems. The CPU usage was going down again. The customer response times also were better. And we thought, great, now we fixed this, everything is good. But then we looked at our graphs again because we like visibility. And what we saw are these spikes. At the top, you will see our response times again, and there were always those spikes, like single requests, where the response times were just way, way higher than for the rest. At the bottom, you see a metric that we have for our static fallbacks. So when those spikes occurred, we also showed the customers those static fallbacks. And this really just is a very simple list of 10 suggestions. No matter what you are typing, for example, you always get washing machine, because this is just a very, very popular query. And we definitely didn't want to show this to the customers because it's just confusing if you start to type trousers and we show you a washing machine. So we try to find out what causes this. And one day, we had some time and started researching and looked up something about spell checking, because our suspicion was that maybe spell checking has something to do with it. Maybe those are wrongly written queries that we just try to correct. And he didn't find anything about spell checking at that point, but he did find another article. And this article was written by Wolf Gabe, and it was about a pruning Redis try. And I hope you remember that we had a try. And this was a Redis try, and it was pruning. So we thought like, wow, this sounds fancy, and this could be really something that we can use. The problem was that this was written in C#, and we don't know that. And also our suggest is written in Python. So as it was, this was of now no use for us. We just couldn't use it. But we still wanted to level up. So before I show you how we managed to do that, I will tell you a bit more about the try structure so that you understand why this was something that we really wanted. So this is a try. In this case, the dark colored nodes are the ends of words. So in this case, we have socks inside, and short and shorts and shirt. This is just one character per node, very simple structure, but worked really fine for our prefix matching case. And now, what is a pruning Redis try? It looks very complex. Don't be scared. I will walk you through it. So the first part is the Redis, meaning you had in the try, you had one character per node. And for the socks branch, there was just one path that went down to the end of the word. So there were no branches going on. So what this new structure does is it takes all the single characters from those nodes and just squishes them all into one node. This is this ox at the top right. Same for the characters in shirt. And this already saves us some space. So this was already kind of good, but this didn't really help us in retrieving the suggestions more fast. And this is where the pruning comes in. And this is basically an early termination algorithm. So you need some input in your data structure to support this, and then your algorithm needs to use this information to be able to figure out when we can stop searching. And this is where those numbers come into play. So what you see in blue are the scores for the entries in our try. So socks, for example, has a score of 30, and shorts has a score of 40. And the other number, the greenish one, keeps track on the children. So each parent node keeps track what the highest score of each of the children is. You can see this in the node with the letter H. This has the max child score 40 because shorts, which is a child in this SH branch, has a score of 40. And this is the highest from the three scores 40, 20, and 10. And based on this score, the children of each parent are sorted. And this then allows us to, when we go there and query this try, for example, if you type S, then we can start at the left because we know at the left is the child that has the highest scores in the subtree. And then we go to SH. From there, we can also go to the left branch. So we go to short. This already is a word, and so we can collect this. And then maybe we want to retrieve 2 suggestions. So from short, we move on to shorts. This is the only child. This is an easy choice. And then we see the score is 40. Now we can already collect those in a sorted manner. So our result list right now would be shorts and then short. Then we can go back up because there's nothing more here. But we already found 2 suggestions and we only want to have 2. So if we look at shirt, the scores are just way lower than the ones that we already have. So now we can go back to the top and we are done, and we have an already sorted list of suggestions that we can just return. This is working with the pruning radix trie. Just as a comparison with the trie structure that we had before, we already had the scores inside, but we just couldn't use them. So if you would have typed S for the normal trie, we would have to retrieve really hundreds of thousands of entries because we have millions of entries in the trie, and then retrieve all of them, then in Python, sort all of them, and then we take 10, which is really not that smart. So with the new data structure, we really thought, okay, this is really, really cool. And because we thought that this is so cool, we gave it back to open source because, as you remember, it was based on the blog post from Wolf Gabe, and the original pruning radix trie also is open source. So this is our open source version. So if you have a Python app and want to use it, you are welcome to do so. And how this looks in production is like this. So the second purple line at the top is the moment when we deployed this pruning radix trie. And our response times just really went down. And this was really good. You can see those spikes that we had for these short inputs completely gone, and our overall response time, even for queries with a bit more characters, also went down. And everything was just smooth afterwards. And our initial goal, the static fallbacks were gone. So now we were really just always delivering something useful to the customers and not just the static fallback that we had as an emergency solution. So this was the last really big change to the architecture that we did. So we want to recap. At the left side, you see how we started with our simple Python app, just everything inside there, the caching and the A/B test logic, everything crammed in there. Then we moved to the separation of concerns, having the distribution with the cache and the A/B tests, and then the business logic in the separate suggest, and then improving something like, for example, the trie, moving to the pruning radix trie. So this really was a very stable architecture then. And now we were really able to work on full customer features. And this is what we will cover now. So C15N. This was a big requirement that came to us in November 2022. So what does C15N mean? C15N means contextualization. Okay, what does that mean? You can think of it as sort of something like personalization, but there is a difference in the way how you look at the customer or how you don't look at the customer. So I will do a little excursus here because I really find this interesting. If we take Tobias as an example, if we would give him personalized suggestions, then we would, for example, get a visitor ID or a user ID that shows, okay, this is Tobias. And then often a pattern is that you can look up some user information in some data structure. This would be personalization because you know, okay, Tobias is asking you and you use the information that you know about him as a person. And contextualization just looks at the context where the user is in. So in our case, this could be, what did this user search for in the past? So what were the past searches? You don't know who did these searches. It could be Tobias searches, it could be my searches. And then you just use this information, but not looking at one identifiable person. This is the core difference between those, and we wanted to do contextualization. So how can we do this technically? As you remember, we had our distribution layer and the suggest, and I already said it a bit, we wanted to use the history. So our idea was we just keep track on the searches that you did in the past. And then we just send them with the request, so the prefix and this history. And then we wanted to apply a machine learning model that should re-rank the suggestions that we retrieve based on machine learning magic, and then give you the best ranking for your suggestions based on the history. Yeah, and then we looked at our pruning Redis try. Still really great architecture, we really liked it, but how can we put a machine learning model inside there? And this was really nothing that we felt comfortable with. So we needed to find a new data structure, something that we can just plug a model in and it just works. And then we remembered last year we were at the Berlin buzzword. And like the buzzword there was Vespa. Like everyone was like, oh, look, it's so easy and it just works. And we remembered it, and admittingly we're a bit careful because often you hear like, oh, it's just working. But if you really try it out, you have to figure out if it's really that easy. But we wanted to give it a shot. And we gave it this shot and did this architecture. So what did we change? You still see the suggest, but on the same EC2 instance, we now have one Docker container running our Python app. This is the suggest. And we have one Docker container running Vespa. And then the suggest, instead of querying our pruning Redis try, it just does a call to the Vespa. And this actually was as easy as advertised. So it took us like a few hours to reproduce this locally, and then really not that much more effort to really bring it into a deployable state. And this is the architecture that is currently running in on AutoDE. So we replaced the try with Vespa because we knew, okay, this gives us the possibility to add a model to our structure. And this is then what we did later. So we trained a light GBM model that you can plug into Vespa because it's basically just a JSON file that you reference. So you tell it, hey, this is my JSON, use it. And then it applied our trained model and re-ranked based on the history. This is everything quite theoretical right now, so I will show you a practical example. What you see here, we will go from left to right. On the left, some user typed W. And this was during winter time, so we have a lot of winter-related queries. And the highlighted ones are winter jacket for men and winter shoes for men. And there's a lot of other stuff for women and a washing machine, because washing machine is just always there. And you have a Christmas tree. But now, in the middle, in the blue, if you have a history looking for a lot of stuff for men, like t-shirts and trousers and watches for men, if you then type W again on the right side, suddenly the red-colored terms on the left are at the very top positions on the right. Because the model saw, oh, there is men inside those terms. Maybe this is relevant to a user that has a lot of men in their history, but still only looking at the history, not knowing who sent us this history. And this is the stuff that we are currently working on. So we are working on tweaking the model and making everything a bit more stable to really be able to bring this to production. And we are also moving a bit more logic from our Python app to Vespa. So you can do some feature calculation and just normal stuff that the search engine could do and that the pruning Redis try couldn't do. So some clustering of our results, for example. And just as a small teaser, we submitted a talk to the Berlin buzzwords this year, and we are praying that they will accept us. So if they do, then we will tell you a lot more about our journey with the machine learning model and Vespa there. So stay tuned if you want to know more details about that. But until then, if you have any questions right now, we are here to answer all of them. And just a little side note, if you want to learn more about the suggest, Alexander Riesen did a very good blog post actually based on a Code Talks talk that we had previously, that this talk right now is also heavily based on. So feel free to also read that. And other than that, thanks for listening, and I hope you enjoyed it.
Fantastic. Thank you so much, both of you. Let me just get to have a quick look at the chat. I think we have some questions already. So, firstly, Florian asks, you only use Vespa to host or serve the re-ranking model, but you're not using it yet to generate the possible suggestions. Is that correct?
No, we are now using Vespa for everything, for serving the generated suggestions and to serve the model. So in Vespa, there's the concept of these two-phase rankers. First, there's the selection phase where you select the matching prefixes. We also do this there. And then we have the first phase ranking, which is some kind of the ranking that which was based on business metrics. We also had that in our old, let's say, pipe pruning Redis try version. And then there's the second phase ranking where we apply the LightGBM model. So we have everything in Vespa.
Okay, Joe Christian Bergen will be very pleased.
Yeah.
Sven has a question. With your suggest application in place and the selection of suggestions based on the pruning Redis tree, what is the role of Elasticsearch? If I got it right, it's not used at all anymore.
Yes. So we removed Elasticsearch completely because so in the past we had a complete Elasticsearch cluster there. It was a little bit too complex to handle this or that. But this was the time when we took over the whole autosuggest. So basically now it's not even in there anymore.
Excellent. Okay. So, well, the Vespa guys will be happy. The Elastic guys will be sad. So somebody wins, somebody loses. That's life. Okay. So Roman has a question. What is the metric you're optimizing the re-ranking model for?
I think that's the MRR. Yes, the mean reciprocal rank. Well, this is a metric which we are using most of the times.
Okay. And that is all our questions so far. Does anybody have another question? You've got a few minutes to type something in to the chat. I'm hoping, hoping you get accepted at Buzzwords. I think that would be a great talk. We are also hoping to be at Buzzwords, so looking forward to that, coming back to Berlin in June. Here's another question from Florian. Can you tell us again the latency and the volume you're dealing with?
So latency is in the low 2-digit milliseconds, so I mean around 30. And requests depends on time of day. So in peak times around 700 per second. So a lot. But actually also with applying the model, it went up a bit, obviously, but it's still, I think the really highest value that we ever had was around 70 milliseconds. But this was also in a time where we were like trying out what we are doing. So right now we are quite stable below the 50 and normally just status quo in the 20 to 30s. Also when we have those peak times with really high numbers of requests.
Okay, great. Thank you. And Roman has another question. Is Vespa cheaper to run than Elasticsearch?
It depends a lot of how you run it. We are running Vespa exactly on the same EC2 instance as our Python application. And in that case, we just need to increase a little bit the memory, and then it was totally fine. So do not have to spend that much on that. But it's cheaper than Elasticsearch. So in the old days, I think you can also run it easily directly on the same EC2 instance, but the options for us, so we compared it a little bit, and it was for us so much easier to store the LightGBM model inside Vespa and to bring it live It's only just a simple configuration. It's 3 lines of configuration, and then you need to add the features here and there. So it was a lot easier for us to bring this whole thing to production.
Okay. Great. I mean, those questions are always hard to answer, and
yes,
extra
yes.
points for using the classic "it depends" phrase, which is the answer to many questions like that. But yes, so Alexander has a question. Is this a massive EC2 single instance or anything scaled out? I mean, he says even 400 queries per second should be doable on a single instance.
No, for sure. I think we will scale out on 12,000 requests or 15,000 requests per second, and then.
But it's not even a massive instance, so it's kind of like kind of a small. It's not even a medium sized, but it's really not one of those 12x large or whatever. That no, way smaller.
Okay. Fantastic. Right. So, do we have any further questions for Tom or Tobias?
If you still have any questions, just feel free to reach out to us on LinkedIn or whatever. So we are available there. Just give us a ping.
We have a last question. So Mario asks, how does Vespa consume data about your products? Do you have a job that indexes data at a regular interval?
Right now we have it kind of statically. So I think the important part is that we don't have products. We only have queries. And with products, you often have the problem that availability or price, and maybe if you store some information about reviews, those are information that change very often. But for our index, the suggestions are really kind of static. So for us, it's enough to just index once a day. And the format that you put into Vespa is JSON-L. So basically 1 JSON per line, and then you just feed it inside Vespa. And for us, this is working really good because of the static nature of our index.
I believe your product search is actually in a different search engine anyway.
Exactly, yes.
Okay, any more questions? I hear the sound of frantic typing. Tushar has a question. Do the suggestions only include prefix-based suggestions or also infix? And if so, how does the data structure handle those?
Yes, that's a very good question. We will have an experiment running in the next days where we also check this. We will also enable infix matching based on a simple regular expression. This is easily doable with Vespa. We only need to change something on the query side, so how we query Vespa. And we currently do not have that feature, but we have it on a feature branch, and we will test it in the next few days to see the direct impact, because we need on every feature a number, and this is pretty cool, but also has a downside that you might be a little bit slow in bringing features live. But yes,
okay.
So it's possible, yes. How does the data structure handle those? As I said, yeah, we've implemented it by just using the regular expression query, which is a feature there. But also all the other search engines can make use of regular expressions in queries.
Yes, of course. There are some people who say you don't need anything other than a regular expression. But there we go. Okay, so Florian, last question from Florian here. Do you have products? I think, Florian, this is, let's see, products that can be split into different categories so that your suggestions could also suggest a category, e.g. Lord of the Rings in DVDs or in books. So
currently we are only suggesting queries. We do not suggest categories or articles directly. And yes, I think this is
okay. Yeah. So the product search is actually in a separate search engine somewhere else. So
exactly.
Michelle asks, does the suggester handle misspellings?
Yes.
This is the short answer. Yes, we are using SimSpell in our application. It's not part of Vespa here, so this is part of the Python API in front of Vespa. We're using SimSpell there with a great dictionary, and so we also have spell check.
Fantastic, fantastic. Great. So I'm just going to give it a couple more minutes if we have some last questions for Tom or Tobias. Tobias? How is it, Tobias or Tobias?
In Germany, it's called Tobias.
Ah, there we go. In English, it's Tobias. So I've completely messed that up.
Yes.
Okay,
It's
so Mikhail says, do you do any sort of a query disambiguation?
So for me, this is some kind of deduplication, disambiguation. Am I right?
Disambiguation, I think it's more about figuring out when you have a query that can mean different things in different contexts.
No.
Mikhail, do you want to clarify your question, perhaps? I mean, do feel free to unmute yourself.
So we do deduplication of queries. So for example, if you type in a P and you will have in your result a PlayStation 5 and a PlayStation 5 console, then these queries are similar, but I don't know if you mean that. So these type of deduplication, this is a feature that we are using, but disambiguation, if you, okay, perfect.
There we go. Deduplication was the problem.
Yeah, we are doing this. And for this, we are currently also developing very hard. We have two approaches there. The first approach is based on clustering, and the second approach is based on a similarity matrix. And we also currently comparing these two approaches.
Right. Okay. All right. Right. So I think we're going to bring it to a close there, unless there's a last question. If you haven't typed it into the chat yet, perhaps something has suddenly occurred to you. Okay. Maybe people can't type fast enough. All right, so I'm going to thank Tom and Tobias. Thank you very much, chaps. That's a fantastic talk there, and looking forward to hearing more. Thank you again for speaking. So the video for this talk will be available on our YouTube channel very soon. I'll also drop a link into the meetup group. But a few other things to mention here. So we haven't got a speaker for our next Haystack Live meetup. So if you do actually have a talk, please go to the Haystack website, look on the right, you'll find a submission link. We do need your talks to keep running these events. Next week, on the 23rd of February, we're running a one-day search event in Krakow in Poland with our partners there, eDrone. There'll be talks about vector search by OSC, voice-powered search, e-commerce search. So do come along. It's a free event running from 2 p.m. Again, details on the Haystack website. On the 27th of February, we're going to Raleigh, North Carolina in the USA. We're having a search meetup with LexisNexis, our friends down there. Talk some Lexis on some of the stuff they've been doing at Apache Solar and from open source connections again on vector search. And then a big one, the week of the 24th of April. This is Haystack US. This is our big flagship conference every year. We've got a whole week of search fun. We've got a search meetup on Monday night, 2 days of conference with 2 tracks, with some amazing talks. And our call for papers is still open till the 27th of February. So if you have a talk, please do submit it. There'll be social events in the evenings, birds of a feather dinners, a new thing for this year, where you can go out and have dinner with people in your same kind of sector or area of interest. On Thursday, we've got a brand new training on search result quality, going beyond search relevance. And that'll be available with a combined ticket with the conference. That also runs into Friday morning. We'll also be having some kind of search hack day, and there'll even be a co-working space if you just want to work somewhere quietly, catch up. And on Friday, we're hoping to do some kind of social event, possibly a wine tour around Charlottesville's, lots of local wineries around there. So come and spend a week in Charlottesville, Virginia. We'd love you to see you, and you can get to know more of your search community. Tickets to more information on Haystack, the Haystack website, and the tickets on sale now at the early bird price. We have also relaunched our Think Like a Relevance Engineer training, as I mentioned before. You can now do this as a self-led course. It's over 5 weeks, starting on the 1st of May for Solar or 1st 20th of March for Elasticsearch. It's exactly the same course with lots of videos, exercises, labs. Do check it out, and it's available at a much cheaper price than previously and at a 50% discount. If you're not already in Relevant Slack, you should be. There's 3,500 amazing search people there, so come and join us there. All kind of subjects. I don't think we've got a sub-channel for autosuggest, but we've certainly got lots of other sub-channels for different areas of search. And again, there's over 100 talks from past Haystack events and other events on our YouTube channel. So that's been Haystack Live. Thanks all for coming. Thanks again to Tobias and Tom for speaking. And we'll hope to see you all again at Haystack Live, where I'm Charlie Hull. I'm from Open Source Connections. We're the search and relevance people. Thank you very much and goodbye.